So we've had an introduction to quadratic residues. We've had 2 lectures on them last week. Now so just a quick reminder, a quadratic residue is a number n in the system of the multiplicative system of congruence classes modulo of prime p. We say a number is a quadratic residue mod p if it has a square root. So in other words, n is a quadratic residue if there are solutions x to this equation, or to that congruence, x squared congruent to n modulo p. Now, we started investigating this, chiefly looking at loads of examples to begin with. And last time we proved this theorem. Well, we kind of discovered it in the examples we looked at, and we proved it last time, which is saying that in these systems, Zp, assume p is an odd prime, so it's some prime greater than 2. There's an even number of congruence classes there. There's p minus 1 congruence classes. Exactly half of them are quadratic residues, and half of them are not. Okay, so that's a very nice, kind of structural result to have. And then on Friday, we got 2/3 of the way proving our other observation from our initial examples. The other observation from our initial examples was that if we took 2 residues and multiplied them, we got a residue. If we took a non-residue and a residue and multiplied them, we got a non-residue. Something which doesn't have a square root times something which does, that can't have a square root. So still to prove is that third possibility, that when you take a non-residue multiplied by a non-residue, you do in fact get back a residue. And you can kind of think of this result as being kind of similar to the idea of multiplying together 2 negative root numbers, 2 numbers which do not have square roots. Well, when you multiply them together, you get a positive number, something which does have a square root. So this final part of that set of results is the equivalent statement for quadratic residues. Okay? So this is going to be continuing on from last time. Now I said to you that this kind of argument was going to be a counting type argument. Okay? So we've already proved. I'm spending too long writing this, but residue times residue is a residue. Non-residue times residue is a non-residue. The writing of the word residue is a bit messed up there. So residue times residue is a residue. Non-residue times residue is a non-residue. So now we assume, or now we let x be a non-residue. Non-residue modulo p. And I'll let x and y be non-residues modulo. What we want to prove is that x times y is a residue. Okay, but on the face of it, it's not so easy just to jump in and prove this directly like we have the other ones. Okay? Because saying x and y are non-residues, that's a kind of a negative statement. It means they don't have square roots. So there aren't these other elements of the system that we can bring to hand and start manipulating. However, but we have to prove that x times y is a residue. Now, the natural thought about how do you prove something is a residue? Well, you prove something is a residue by exhibiting its square root. Finding a number such that when you square it, you get x times y. But that direct approach seems to be a bit difficult to get started here because our assumption about what x and y are is a kind of negative assumption. It doesn't give us any objects out of which we might construct the square root of x times y. Okay. So we're going to prove this in a different way. And you can kind of think of it as a proof. Well, it's not. We're not going to present it as a proof by contradiction, but one could do that. We're going to phrase it as a type of a counting argument. So we'll use a counting argument for this. So what do we know about residues and non-residues? Well, we proved exactly half of the elements modulo p are residues, exactly half of them are not. We've also proved, look up here, that non-residue times residue is a non-residue. So let's think about this. If we consider, well, let Z1 to Z p minus 1 over 2 be the, what do we let these? We'll let these be the residues modulo p. I should have called them R. Yes? What's a residue? A residue is a number which has a square root modulo p. It's a square modulo. Okay, if we let Z1 up to Zp minus 1 over 2 be the residues modulo p, then each product x times Zi, so we're assuming x is a non-residue, each of these products, x times Zi, this has to be a non-residue. Okay, as we proved earlier. So when you multiply x by the residues, we get all the non-residues. But that's the key point. We get all of the non-residues. So certainly each x zi is distinct. Each x times zi is a unique element from all the other x times zi. Okay? When you multiply any pair of these residues by x, they can't give you the same product because you can just cancel the x from both sides and then the pair would have to be the same. So each of these x times zi are distinct. So they are all of the non-residues. Okay. All of the non-residues. So now we're dealing, remember, with two non-residues, x and y. So what are the options for x times y? So considering x times y, you see that xy is certainly not equal to xzi for any I, since y is a non-residue. See, y is a quadratic non-residue, so it can't be that x times y is equal to x times the zi for any of the i's, because if that were the case, you can just cancel the x's, but then you'd be saying that y was one of the residues. So what's the only remaining choice for this? Because we've already just said that x times a residue is a non-residue, and x times a residue, when you go over all of the residues, that accounts for all of the non-residues. So what we're saying is x times y, it can't be a non-residue, because they've all been used up Okay? When we take products with x, when you multiply x by the residues, each of those products has to give you a non-residue. Proved that last Friday. So when you come to multiply x by a non-residue, it has to be a different element from any of these elements, x times zi that we've looked at. It can't be the same because you could just cancel the x's and then y would have to be one of those. So when y is a non-residue, you multiply it by another non-residue. All the residues are already used up in these products here, so the product has to be a residue. So it comes out from that kind of counting argument. Okay? All the slots of the non-residues are already used up by these products. So when you come and look at a product x times y, both of them are non-residues, that product has to be a residue. So therefore, the only possibility, and this is something, remember, we've observed in all the examples we've looked at so far of the different primes, looking at how the non-residues multiply together. When you multiply two non-residues, you get a residue. The only possibility that x times y is a residue. The writing of the word residue comes out wrong. Sorry. So that finishes off that final case, that set of three results that we were proving last time. So the way to remember these results is they very much mirror or look like the results of positive times positive equals positive, negative times positive equals negative, and negative times negative equals positive. Those familiar results about real numbers is replicated here in the case of quadratic residues and non-residues modulo p. Okay, any questions about that argument or things that I can clarify for you now? Okay then. So that's good. We've got some initial results. Half of the elements are residues, half of them aren't, and we kind of have this structural thing about how they multiply together. So I'd like to look at now is this definition 8.2. It can become a bit, this is definition 8.2 at the bottom of page 56. It can become a bit unwieldy all the time to keep on talking in phrases, this is a residue, this is a non-residue, and so on. So to just make it a bit more compact and efficient, we introduce this notation. This notation is called the Legendre symbol. And all it is, well, all it is at the moment when we look at the definition of it, it's just simply a piece of notation just to indicate which things are residues and which things aren't. So we present it as this bracket symbol. So n and p in brackets separated by that straight line. So that's called the Legendre symbol of n and p. And it's understood to have two values. So the n is an element of a congruence class, of the set of congruence classes modulo p. And we think of n as coming from the group, the multiplicative group of congruence classes modulo p. So it's one of the elements 1, 2, 3, 4, 5, etc. up to p minus 1. So non-zero modulo p. And the Legendre symbol np simply takes the value plus 1 or minus 1 according to whether or not it is a quadratic residue. Okay. So it's just some compact little piece of notation. So we can write brackets np, the Legendre symbol np equals plus 1. That will indicate it's a quadratic residue. And if we write it as np equals minus 1, that will indicate it's not a quadratic residue. Now, if that was all it was, there wouldn't be a whole lot of point in it. But it's going to help us think about and kind of structure our analysis of this general problem, because there's the general problem floating around is given a pair of numbers n and p, is n a quadratic residue modulo p? That's a general problem floating around, which we don't have any understanding of at the moment, apart from the cases where n is obviously a square, where it's already a square integer. So this is the kind of looming problem at the moment. And so in terms of this notation, it seems you can easily write down the question, is np plus 1 or minus 1 to the Legendre symbol? But it immediately, what it does do is it does immediately give us just forming the notation like this, kind of it forces us to think about it like a function. So immediately we can think of this function where, okay, you've got p in the second place, but the argument of the function goes in here in the first place. And then it's a function from the set of congruence classes modulo p to the two element set plus and minus 1. And answering this question of when is n a quadratic residue modulo p, that then becomes a question of understanding how this function behaves and understanding or trying to get results about how we might evaluate this function on any given argument. Just gives us ways to think about the problem. So just for the sake of completeness, if we do ever encounter a Legendre symbol np where n is 0 modulo p, then we'll assign the value 0 to the Legendre symbol. But really that won't come up a lot, really. So looking at some examples, if we think back to the example of the prime p equals 7, when we looked at the prime 7, so there's 6 congruence classes, 1, 2, 3, 4, 5, 6, we found that 1, 2, and 4 were quadratic residues, and 3, 5, and 6 were not. So you would record that by saying any of these Legendre symbols is plus 1, and any of those Legendre symbols involving 3, 5, and 6 has to be in negative. Now, just while we're on the subject of notation, this way of writing the Legendre symbols is about what half of authors do, or about half the time you'll see them written like that. The other half of the time, you'll see them written in this kind of fractional form here. So you do a fraction n over p, and there's a pair of brackets around it, and you're meant to understand that as the Legendre symbol. Okay? Obviously, it's just purely arbitrary whether you write it in a row or a column. It's just a piece of notation, but just something to be aware of. I've avoided that notation just because it would kind of force you automatically to start thinking about fractions and the fact that p is in the denominator, and that's kind of misleading. I don't think it's any fruitful way to think about it like that. So that's why I've avoided that notation. But of course, the notation we're using, it's got the slight drawback is that it reminds us of the divisibility notation. Because if you saw that without the brackets, you'd read it as saying n divides p. It'd be a funny looking statement anyway, because p is a prime number, so you should really be talking about things dividing p, apart from 1 and p. But when there's the brackets around it, it becomes a different piece of notation for the Legendres. It's unfortunate, but you know, those are the types of notations in use. So these are the ones we're going to do. So, as I've said, having this notation, if we fix p, then we can think about it as a function with where the argument goes in the first position. It's a function from zp to plus 1 minus 1. We can start to try and understand this and prove results about it. So straight away, here's a couple of results about it. Lemma 8.2 and theorem 8.3. And the proofs of these won't take us very long, because the first one is obvious. If you ever see a square integer in the first position, in the Legendre symbol, well, clearly that has to be take the value plus 1. Okay? Because to evaluate this Legendre symbol, you ask yourself, well, is m squared a quadratic residue? Is there some number such that when you square it, you get m squared? Yeah, of course it is. It's n. Yeah? So it's declaring itself to be a square. So the Legendre symbol will certainly take the value +1 when you evaluate it on any square integer. Okay. Secondly, we get this rather nice result, which looks a bit unfamiliar, but in fact it's what we've been doing when we've been proving these three cases here. And that is that the Legendre symbol is multiplicative. Considered as a function in the first position, it's what's known as a multiplicative function. So a multiplicative function, it's like a function being linear, except being linear refers to an addition operation in the arguments of a function. Being multiplicative just refers to the multiplication argument. Okay? So a function g is multiplicative. What that means is that when you evaluate g on the product x times y, it takes the value g of x multiplied by g of y. It's a nice property for a function to have. It says that a function fits well with the operation of multiplication, whatever that particular operation of multiplication should be. And a nice, clear example of one you're familiar with is from the setting of linear algebra, the determinant function, which applies to matrices. The determinant of a product of matrices is indeed the product of the determinants. And it's a clear example, an important function you're aware of in another setting, which you describe as being multiplicative. Well, here we're saying that the Legendre symbol, considering it for fixed prime p, so considered as a function in the first argument, is a multiplicative function. So that's saying the Legendre symbol of n times n is indeed the product of the individual Legendre symbols, Legendre symbol of n multiplied by the Legendre symbol of n. Now, the proof of that is really just the result about multiplying different types of residues and non-residues, just the three cases that we've gone through last Friday and today. Okay, because the options for this thing here. The options for this thing here are either, on the left-hand side, they're either plus and minus 1. That's what the Legendre symbol is defined as. And so the options for these two factors here are plus 1 or minus 1. Okay. So if n and m are both residues, both these numbers will be plus 1 over here. We proved that if n and m are residues, then so is the product. So this will be plus 1 on the left-hand side. If one of them is a residue and one of them isn't, then one of these factors here will be plus 1, the other one will be minus 1. Well, we proved that the product of a residue and a non-residue is a non-residue. So the product n times m will be a non-residue. So you have minus 1 here. Again, that agrees. Minus 1 is plus 1 times minus 1. The last case is where they're both non-residues. So when n and m are both non-residues, these two Legendre symbols on the right-hand side, they're both equal to minus 1. So they'll multiply together to give you plus 1. But we've proved that the product of two non-residues is a residue. So we started off today proving. So the negative 1 times negative 1 gives you plus 1 on the right, but you also have plus 1 on the left by the definition of the Legendre. Okay. Now there's a proof in the notes there, which is slightly different version. It isn't kind of worded so much like that, but that exercise, which we discovered in the examples we looked at and which we proved last Friday and today, that gives you the proof of this this problem. Okay. So, as I say, that a lot of the rest of the chapter is kind of based on this task of evaluating the Legendre symbol MP. Now, before we proceed with any more of the results from the book, I'll just kind of make an observation now. about what we already know. So if you consider the problem of evaluating NP, consider this problem. Now n is an arbitrary integer, co-prime to p. Well, since we're in a number theory course, there's a very obvious way to think about an arbitrary integer. And it's quite important. I mean, we gave the results. It's called the fundamental theorem of arithmetic. Every integer is a product of primes. And that has been quite useful for us in a number of different areas. Okay? So if this is the prime factorization of n, the product of a bunch of prime numbers raised to various powers, when you apply that to the problem of evaluating the Legendre symbol, suddenly you make a little bit of progress, or you make a kind of a breakthrough. So p is some prime number, n is a product of primes pi. Now we'll assume that none of the PEI's are equal to p. So we're assuming that n is a number co-prime to p. So we're assuming that it's representing a congruence class in the multiplicative set of congruence classes in modulo p. But you see, we've just proved, we spent time last Friday and today, we proved that the Legendre symbol is multiplicative. So here's the Legendre symbol, evaluated on a number n, but the number n is written as a big product. Product of all these powers of primes, and powers of primes are themselves products. And we just quoted the multiplicative property as being, when the argument is one number multiplied by another, then the Legendre symbol factorizes. But of course, that's where a product of two factors, but of course that would generalize to a product of any number of factors. So straight away, we get this nice result that evaluating this Legendre symbol just comes down to evaluating each of these individual Legendre symbols, because it will break that down as the product. Excuse me. This Legendre symbol will factorize into the product of these Legendre symbols. This is all just the operation of multiplication going on, different factors in the first position. So what this little observation shows you is that the problem of evaluating any integer, the problem of evaluating the Legendre symbol on any n, really it boils down to knowing what the Legendre symbol will be on any prime number, modulo p. So in a way, it's enough to know the residue status of all the primes less than p. Or no, it's enough to know the residue. It's enough to be able to answer this question of what's the residue status of one prime modulo another one. If you can answer that kind of question, then armed with the prime factorization of any integer, you can then answer the question of what's the evaluation of the Legendre symbol of n on p. So that is kind of in the background. We kind of hold that kind of thought in our minds. Okay. So we'll see. We'll see the relevance of this observation later on in the chapter. Okay. This will be the route through which we'll be able to answer this general problem of how to evaluate the Legendre symbol on any n. We'll be able to answer it by boiling the question down to what's the residue status of one prime modulo another one. Okay. But now this chapter is, we come at this problem in a few different ways, and build up a number of different results about evaluating the Legendre sum. So the first one is theorem 8.4, which is Euler's criterion. And in some ways, this looks like it gives you a nice formula for it. And it kind of looks like the end of the story, except there are problems of evaluating it for large arguments. Okay? Now this builds on something we already know about. So we'll recall Fermat's little theorem. Okay, or we also referred to this result as Euler's theorem. I think John refers to it as Fermat's theorem. I kind of referred to the generalization of it as Euler's theorem. But this says that if a prime number p does not divide the number a, then a to the power p minus 1 is always congruent to 1 modulo p. Euler's theorem stated it more generally, said that a to the power of phi of m, where phi was the Euler-Toshin function, was congruent to 1 modulo n. Well, in the special case of a prime, this was, we call this Fermat's theorem. Okay, so this is known to us. We've used this a lot, this idea, or the generalization of it in Euler's theorem, that lay behind one of the coursework problems, simplifying those large powers of 2099 or whatever it was. Use the Euler-Toshin function for that. Now, how might we relate this to the issue of quadratic residues? Well, the thing is, if we're dealing with a prime number greater than 2, this number, p minus 1, is an even number. Okay? So if p minus 1 is an even number, then that means we can immediately take the square root of this. The square root will be simply a to the power of p minus 1 over 2. So you take the square root of a large power by just simply halving the number of factors in the power. So we can write that a to the power of p minus 1 over 2, when you square it, you get 1 modulo p. P minus 1, p is a prime number greater than 2, so p minus 1 is even, so it's okay to write p minus 1 over 2 as the exponent there. That is just an integer exponent. Well, you see, that's the same as saying that, see, what are the square roots of 1? Well, it's only got to, remember carefully the justification. We've already proved Legendre's theorem, which said that a polynomial congruence modulo a prime, it has at most, well, this one would have at most 2 solutions. 2 is the degree of the polynomial. Something squared is congruent to 1. How many solutions does that have? Well, if it's modulo a prime number p, Legendre's theorem tells us it's got at most 2 solutions. Well, because this is congruent to 1, something squared being congruent to 1, it does have the solutions plus and minus 1. So we can confidently say then that if this is true, then a to the power of p minus 1 over 2 must be congruent to plus 1 or minus 1 modulo p. And this is true for every congruence class A. Every non-zero congruence class A modulo p. Is that okay? Any questions about that or queries about that? So simply observing Fermat's little theorem tells us a to the power of p minus 1 is congruent to 1. So you simply take the square root of both sides. So a to the p minus 1 over 2 must be plus 1 or minus 1. modulo p. But now we've just gone to the trouble of introducing our Legendre symbol, which is something which takes the values +1 or -1. So suddenly here we've got, well, let's call this A. So is A a quadratic residue modulo P? Well, we're going to write this equals +1 if it is, and -1 if it isn't. Here we have a little expression in A to the power of P minus 1 over 2. We know it's congruent to +1 or -1. So it's tempting to kind of say, well, this is congruent to +1 or -1. Maybe that will be the same. Maybe the value + or -1 we get out of this, the Legendre symbol, will be the same as the value + or -1 we get out of this. Now, the first time you see it, there's no particular reason why this should be the same as that. But this is to do with powers, and it's got a half, so maybe it's something to do with, it's come from something to do with squares. So this suggests there might be a link. So suppose the Legendre symbol is +1. Suppose it is a quadratic residue. Well, what is that? If something is a quadratic residue, it means there exists a square root for it. A is congruent to b squared modulo p for some b. So we're assuming we get +1 out for the Legendre symbol. Well, what are we going to get out for this? A to the power of p minus 1 over 2. When you go a to the power of p minus 1 over 2, well, you see, we're assuming a is b squared. So simply substituting b squared for a to the power of p minus 1 over 2 is going to be b squared to the power of p minus 1 over 2, or congruent to it at least. But of course, then the 2's will cancel. We're taking b squared to the power of p minus 1 over 2, well, that's just going to be exactly b to the power p minus 1 modulo p. But then Fermat's theorem applies. We've got something raised to the power of p minus 1, so that must be congruent to +1 modulo p by Fermat's little theorem again. That anything raised to the power of p minus 1 is congruent to 1. So if A starts off by being a square, by being a quadratic residue already, when you raise it to the power of p minus 1 over 2, you have to get +1. Well, that's good. So we've argued that a to the power of p minus 1 over 2 gives you +1 or -1. This Legendre symbol is set up to give us +1 or -1. So if it's plus on the Legendre symbol, it must be plus on evaluating this power. So it very strongly suggests then that if it's negative on the Legendre symbol, then it should be negative on the power as well, one would hope. Then we need to prove this. On the other hand, suppose this time that A is not a quadratic residue, so that the Legendre symbol AP is -1. What we want to show is that a to the power of p minus 1 over 2 has to be -1. We know it's either +1 or -1. So we just have to rule out the case that it could be +1. And again, this is a counting type argument. Okay. But again, it's a counting argument. So we're considering a to the power of p minus 1 over Again, it's a counting argument. If we consider the polynomial x to the power of p minus 1 over 2 congruent to plus 1 modulo p. Legendre's theorem, let me just get the number of that for you. It's back in Lagrange's theorem, back in theorem 7.1. Says this polynomial has at most p minus 1 over 2 solutions. And look, Lagrange's theorem says the degree of the polynomial congruence is an upper bound on the number of solutions that it might have. But it's a polynomial congruence modulo of prime. So Legendre's, I keep saying Legendre instead of Lagrange, excuse me. Lagrange's theorem says that this polynomial has at most p minus 1 over 2 solutions. Well, we've already filled up all those possible solutions. We've already shown that whenever A is a quadratic residue, it is a solution to this polynomial congruence. And we know that there are p minus 1 over 2 quadratic residues. So all the available slots for solutions of this have already been filled by all of the quadratic residues. So the non-residues just have to go somewhere else. Okay? There's no more room for them to be solutions of this as well. Okay? Because we know that all the slots have already been filled. Okay? Just seen that all the p minus 1 over 2 residues are solutions. So if AP is minus 1, if it's not a residue, then A to the power of p minus 1 over 2 cannot be congruent to 1 modulo p. There's no more room for it. But we proved already that it has to be plus 1 or minus 1. See, we observed by talking about the square roots of plus 1 being plus 1 or minus 1, we already observed at the top of the screen there, A to the power of p minus 1 over 2 has to be plus 1 or minus 1. So if we've just said it can't be plus 1, the only option is it has to be minus 1. So then A to the power of p minus 1 over 2 has to be congruent to minus 1. So that, what we've just gone through there, is the proof of Euler's criterion. Which says that the Legendre symbol AP is congruent to A to the power of p minus 1 over 2 modulo p. So in some sense, this is theorem 8.4 in the notes. Proof is all written out there in the notes, but it's the main points of it we've gone through here on the board. In some sense, you can kind of say, okay, well, that's the end of the story. That's the solution to the problem. How to evaluate a Legendre symbol and any input A, we just work out A to the power of p minus 1 over 2 modulo a prime number. However, this still has the drawback that this formula, while it gives you the answer, it's going to become increasingly hard to evaluate. As the primes get larger and larger, this exponent is going to get larger and larger. So you start to run into computational difficulty with evaluating this, you could say. And also, it's only kind of one view on it. Knowing this formula doesn't immediately offer up a complete understanding of it. So it's a nice compact formula, But if you're given any particular A, you just have to go away and work out this, and then boil it down and see if you end up at +1 or -1 eventually when you're working at this large exponent, large power of p. Okay. So it's fine and good as far as it goes, but we kind of seek a much deeper understanding of these Legendre symbols. Where we're really aiming for is the understanding of this question of what is the residue status of one prime modulo another one. And the solution of that problem is kind of what we're building up to towards the end of the chapter. Okay, so we'll leave it there for the moment. There's a bunch of the initial end of chapter exercises are available to us now. Pages 67 and 68. I think about up to exercise question 7, I think. So that will occupy us for the tutorials this week at least. And we'll have 2 lectures on this next week. Okay, so we'll make some more progress with this next week.